So basic steam water cycle, all right, can be broken up into these 4 different sections here. All right, we start off with our generation, and then we go into where it is used, and then it's condensed, and then it comes into feed water. All right, so we start off with our boiler. From our boiler, it goes to the superheater. From the superheater, it splits off into 3 different sections. We have our auxiliary, our TG, and our main steam. All right. When we talk about the main steam water cycle, we're going to only continue down this line. Our TG steam goes to what, probably? What would the TG steam lead off to? Right now we're covering propulsion, but what else do we use that steam for? That would be sending off to our turbo generators, our TGs. All right, so that's where our steam goes off to our, basically where we're going to create electricity. All right, and then our auxiliary steam, that's going to be going off to all of our auxiliary components. All right, so we talked about heating into that glycol, all right, for the freshwater generation plants, stuff like that. Okay. So from there, we continue on into our HP turbine. From our HP, we go right into our LP turbine. All right. From there, it sucks directly into our main condenser. At this point, we are done with propulsion. We have done from generation to main condenser. We have done the job of what the steam was boiled and turned into a vapor was for. All right. From main condenser on, it's all about squeezing that energy out of it. All right. How can we gain any sort of efficiency back? Because if we just dumped it out to sea from our main condenser, we would have very little efficiency. And steam plants are actually very, very efficient once you start adding all of these components into it. All right. So from the main condenser, we go to the main condensate pump. Where are these main condensate pumps located? In the engine room. They're going to be right next to the main condenser. All right, so if this circle right here is our main condenser, we have our stairway to go up the next level to the main engine room. We have our atmospheric drain tank over here. And we have our doorway into the engine room right here. All right, our main condensate pumps are located center line of the ship, forward of the main condenser. All right, those 2 pumps are your main condensate pumps. From there, they go to your air ejector. All right, that's located on the main engine room level, starboard side. Oh, I'm sorry, port side. I got myself flipped around. Port side. All right, so if we're on the upper level, you have your lube oil strainer right there. You have your burner bench over here. It's located as forward as you can get before you hit those switchboards. That's your air ejector right there. From there, you go to your first stage heater, which is located on the lower engine room. Right next to the door going into the lower engine room. All right. Go all the way up to your DC heater, which is located as high as you can get in the engine room. Looks like a giant soup can. And from there, you go way back down to the lower engine room to your main feed pumps, which are located in the lower engine room, starboard side. And you have your main feed pumps. You have 3 of them. One is your in-port feed pump, and that's located as far starboard as you can get location with your feed pumps. The 2 others are located forward and aft of each other on the starboard side, and they're both turbine driven. All right. From there, you go to your economizer, and your economizer is located inside of your boiler. All right. So, like I said, you're split at these sections. From your boiler to your main condenser is all the vapor side, and from your condenser into your boiler is all liquid. All right, so take a look at whole mess of numbers. All right. The biggest thing here is that we should take a look at are a couple of things. First of all, we should be looking at how high of a pressure is leaving our boiler. All right, you guys shouldn't have this number almost memorized to the point where you know your 600-pound steam. It's coming out of your boiler, and that's your main steam line there. All right. And as it comes through, the big thing to pay attention to is not to have these numbers memorized, but the understanding of what is happening there. Why your high pressure turbine is so much smaller than your low pressure turbine, and how you're getting almost the same amount of force and usability out of your steam in both. Whereas your high pressure turbine is built to withstand and take these high temperatures and these high pressures. It's 585 PSIG before it hits that high pressure turbine. And when all of that energy is used, and right before we go into that low pressure turbine, it's only sitting at 440 PSIG, and we're getting the same amount of energy coming out of that. That's something to just always keep in mind of what's happening inside of these systems. All right. The other thing that you really want to look at is what's happening here. Your DC heater is sitting at about 15 PSIG, and it's way up as far as you can get in the engine room. And that's to give it as much head pressure as you can possibly give it. All right. It's to add more pressure and to help out this feed pump, because this feed pump's job is to spit out water at a super high pressure. Because where is it going? It's going right from the feed pump. It's got to go into the economizer, and from the economizer, it's going right into the boiler. And that boiler is sitting at 600 PSIG. It's got to overcome that pressure. And it's not going to be at that same pressure. It's going to just dribble in if it's at the same pressure. You need to have it over pressured so that way it can overcome that force. All right. These are why these numbers are here, is to give you a frame of reference to make you think of what's actually happening in the system. Every single one of these numbers is a reason it's there. Let's talk about the generation cycle first. So we have our drum type boiler, all right? Like I've talked about before, these will go into depth come your freshman cruise, all right? But the big thing that you should understand about is where the air is coming in, where your fuel is located that it comes in and enters. What's the, the main principles of where your feed water is being entered into the boiler? Where's the steam being generated? All right. So air is located and basically comes in between the boiler the boiler wall of where you would think of where the flame is, where the inside of the boiler is, and the outside wall. There's a pocket there where the air gets preheated by the furnace and it comes in and it gets sucked in that way. All right. That adds some efficiencies. It also keeps the boiler from becoming too hot. All right. As far as like what you're concerned about it being on the outside of it. All right. And then you enter fuel into your boiler and that produces your flame. Your flame exists in this area. All right. It's almost like a cone that comes straight out. It's pretty intense to see. So that's where you actually have your ignition and your fire and what people have with what they think about where the burner is. All right. And those, any of those like any of the fuel, any of the heat generated, anything that is just associated with the burner is going to travel up and it goes through all of these tubes and out through the stack. All right. Remember, it's going to basically all encompass this area. All right. So, biggest thing in the world, does steam come out of the stack? True or false? What comes out of the stack of the TSES?
It's
Say again? If I said to you that steam comes out of the stack of the boiler, is that true?
yes.
No. So remember, what we're trying to do is we're trying to keep any of this steam, any of the feed water, we're trying to recirculate it as much as all of that stuff is valuable. All right. We're not going to just be putting it into our turbines and then shooting it out to atmosphere and being done with it. All right. The only time steam would be coming out of the stack is through the steam whistle. All right, those fog whistles that we have. All right, that's the only time that would be true. But for the most part, the only thing that's going to be coming out of the stack and why it looks like steam, all right, and why a lot of people have that misconception is one, because it looks pretty clear when it's running. People would think a steamship would be running dirty. And two, they think like a steamship, they think of basically of like trains, and they don't reuse their water in trains. They basically use it, they're done with it, they dump it. All right. So the only thing that's coming out of the stack is going to be soot. All right. All of the expelled gases, all of basically whatever is a byproduct of the flame that's inside of those boilers. All right. So we have a couple drums located in the boiler. We have our steam drum, we have our water drum. In the bottom left over here, we have our mud drum. Whoa. Okay, that's a new thing. We have our mud drum. All right. And then we have our generating tubes. They're located in yellow here. All right. What I'm highlighting here in red is not part of the generating tubes. All right. They're on the outside of what I just colored in red. On both sides. You can see there's kind of a wall of it, and then there's a bigger mass on this side. All right. And what's happening is what I just colored in red is our superheater. So this, basically, if you look, there's like almost 2 tubes there, where this has like probably close to like 16 or something like that. The those two tubes, what their job is to protect the superheater in there. We'll talk about why in a little bit, but that's really what that's job is that these tubes are filled with water, these generating tubes. All right. If you look at it, your steam drum is half filled with water and your water drum is obviously filled all the way. But you have all of these tubes that have water in it that can just take a huge amount more heat than what's going to be in those superheaters. All right. And inside of these generating tubes is basically that's where the majority of your steam is going to be generated. Yes, of course, you can have steam generating elsewhere, but the main part of your steam is going to be coming out of these generating tubes. All right. You have your water wall tubes. Your water wall tubes are basically there to try and keep the heat and the boiler inside. All right. You're trying to utilize the liquid, the water that's already in there to protect the outside of the boiler. All right. And you're using the water wall tubes, and that's one of their main jobs is to keep the heat in. All right. It's almost like insulation, but instead of just putting foam and using foam to keep the insulation in, you can actually generate some steam out of it. All right. So you have like a flow of water that happens inside of these generating tubes and these water wall tubes. Basically, they're in this circular motion of sorts. All right. And what's happening is that in certain spots, the flame will come in and you would have a steam droplet form here. And it would travel up a little bit. And as it travels up, it's giving off heat because everything in the world wants to be equal. All right. And as it's giving off heat to all the other water molecules around it, all the liquid water molecules, it can lose that heat and not become a vapor anymore. And then it will just sit at this point as a liquid. But as it travels up, it may make another water molecule that's a liquid turn into a gas, and that will fly up higher. All right. And that kind of ballet is happening all through these water generating tubes. And as it comes up, it may heat up in here, it may fall back out. All right. And as it gets cooler and it gets more dense, they'll fall back down. All right. And it just kind of follows this circle. Now, we are producing steam, but it's not like this water molecule that sits all the way down here is going to journey all the way up and go into our turbo generators just like that. And it's all very nice. All right. Inside of there, it's just very much a ballet of water becoming steam and then coming back into a liquid and then going back to steam and then coming back down. All right. But the circulation mostly looks at what we're having here. So as I talked about, we have our superheater in the middle. That's where I painted red earlier. And what is in our superheater but only steam? All right. Only thing that goes into our superheater is just pure steam. So as it travels through, it's going to become hotter and hotter. And it's basically, if you think about it, like we talked about refrigeration, the only time you can go up in temperature after a change in state is if you remove all of the previous state. All right. If you're going to go from a solid to a liquid, when you're in that latent heat of solid liquid mixture, before you can start to increase your temperature of that liquid, all of the solid must be gone. All right. And the same thing goes from liquid into a gas. All right. And that's what our superheater is about. We are increasing the temperature of our gas, of our steam. All right. So there is no liquid present. And if there is, It's all gone at this point. All right. So we are increasing the temperature, and we're going to be exiting as a high pressure, high temperature gas. All right. 600-pound steam at like 800 degrees. It's so hot and it's such a pure steam that you cannot see it. If there's a steam leak, you physically can't see it. There's no way, there's nothing for the light to bounce off of to give you a visual representation of what's actually there. And that is why these generating tubes exist. And there's only 2 of them right here. They're basically just protecting the superheater. All right, if that superheater was exposed to pure flame, it would probably melt. So those tubes on this side of the generating tubes are just there to keep the superheater. It just gives it that little bit of buffer that it needs. So from the superheater and out of the boiler. Now, the big thing is I want to talk about, we'll only talk about one boiler right here. This is the one instance on a ship where we don't have a backup. All right. We can steam with one boiler, but it's not really. Like, we're always going to use both boilers at full capability the entire time. All right. And if you go on a steam trip, that's what you're going to be doing when you leave maritime. All right. You're going to be utilizing both boilers, and that's what it's designed to be doing. You can steam on one, and you can be propulsion, but it's very limited to what you can do. All right. So just remember, you have both boilers doing both things here. So out of the superheater and into your piping. And from there, you have your main steam stop valve. You have your TG stop valve, as we talked about, that goes directly to your turbo generators. That's how you're producing your electricity. And you have your auxiliary steam stop valve. All right. And like I said, goes to the Nyrex, heating up fuel, this, that, everything, all that good stuff that we talk about. Auxiliary steam comes in here. Auxiliary steam comes in there. That's where that auxiliary steam is coming from. All right. It all starts its life at 600 pounds, 800 degree Fahrenheit steam. And then we have our superheater safety valve. All right. We also have our superheater vent valve. One is automatic. This one is a manually operated valve. All right. So that is our boiler superheater out to our TGs, auxiliary steam main steam stops. All right. Any questions on this generation section before I continue into turbines? Everybody all good? All right. So let's talk about turbines. This is an axial flow turbine. What we see here is basically we have like this nozzle right here, and it's basically just a very simple, like, you can blow into a pinwheel kind of thought process with what we have here. All right. And what we're looking at is we have our steam velocity, and this is a representation of what's physically happening in this space. So, I want to erase everything. So what happens is as our steam velocity is increasing through our nozzle, all right, we will hit a peak when we exit that nozzle. And from the nozzle to when we hit the first turbine blade, we're steady at that velocity. And once we hit that first turbine blade, we start to decrease in our velocity. All right. And what we're doing is we're imparting energy onto the turbine until we leave the turbine blade and we peter out. So we can't just create this energy from nothing. So we're using basically our steam pressure. So it has the reverse effect. It has a high leading in to the nozzle. And as soon as it hits that nozzle and we start to increase our velocity, we are going to be decreasing our pressure. So where we're giving up pressure, we're increasing our velocity. All right, same thing again. As soon as we depart that nozzle, we're pretty much done giving up our pressure. It's a little bit more pressure to give up because then we hit atmospheric over here. All right, and then we stay steady for the entire rest of this. All right. Does that make sense to everybody? Good. So this is our HP turbine on board the TSES. We have a 3-stage impulse turbine. All right. We have nozzles on each one of our stages. All right. I hate when this happens. We have a nozzle on each one of our stages. All right. And a stage consists of a nozzle and a turbine blade. All right. The nozzles are stationary. They do not move. They stay there for their entire life. They're bolted in. They don't move until the ship is turned to razor blades. That's them for their entire life. All right. They're fixed nozzle diaphragm attached to the turbine casing. All right. The blades move and they're fitted to an axle. All right. And that axle is what's going to be propelling and actually doing the propulsion of the ship. All right. And like I said, a stage consists of a nozzle and a blade. That is a stage. All right. And that's how we have a 3-stage impulse turbine. And again, this is our HP turbine right here. We have come out of the boiler, and this is the first thing we hit. Well, technically, we hit the throttle box, but that's another story. And as we can see here, the same effect is happening. We're losing pressure through it, but we're gaining velocity. And each time it goes through these nozzles, we lose a little bit of that pressure, but we gain some velocity. And the next nozzle set does the same thing. And next one after that. And that's why our blades are going to be bigger and bigger and bigger. So more energy can be imparted on it because all of these are attached to the same shaft. All right. And there's a cool little animation. Number 2. So those are coupled into our reduction gears. We'll talk about that later in our steam PowerPoint. So from our HP, we go to our LP. All right. And this is what we're really looking at here. All right. We have something called a steam chest right here. That steam chest is what you would think of like we talked about a sea chest. That is going to be where all of your steam that's going to be entering your HP turbine, it is flooding that steam chest. So that steam chest is going to be full of all the steam. But we have something called nozzles on the TSES that will be able to control how much that steam enters the HP turbine. All right, so they're basically just throttle valves that will open or close that allow steam to go in. All right, but that steam chest, if you think about it, is going to be full of steam. All right, and from there it goes into your HP turbine casing. from your HP turbine casing, it goes into your crossover. And now here's the biggest thing that we want to talk about. A head steam. When you are going ahead, your steam will go through your HP turbine to your crossover, into your LP turbine, and down into your main condenser. Always. All right, and if you're going to be using a stern steam goes into your LP turbine, down into your main condenser. You can almost draw a line right here where a stern steam exists only on this side of it, and your head exists on this side. There is no physical barrier, but what is happening inside of it is the drawing of that low pressure condenser. That condenser is almost at a perfect vacuum, and we have such a high pressure in this LP turbine that it's going to be sucking whatever comes its way down in there. So again, a head steam will only go to the HP turbine casing, to your crossover, to your LP turbine casing, and down into your main condenser. A stern steam will just be going through the stern steam section of the LP turbine and down into your main condenser. All right. So your HP turbine, 9 impulse stages. Like I said, it has its steam chest, and there's your crossover. You have something called an HP turbine bleed. It's in its 6th stage. So you have your 1, 2, 3, 4, 5, and 6. All right. You have your IP bleed crossover extraction. Like we talked about, some of this is used for startup. Some of it is used in systems that we no longer use. All right. But just know that they are there. And steam will basically exit your steam chest and fly through all of those stages into your crossover to the LP turbine. Now, in your LP turbine, you have 4 impulse, 1 transition, and 4 reaction. All right. So here's your 4 impulse right here. 1, 2, 3, and 4. You have 1 transition. So your transition is right here. And then your 4 reaction stages. All right, so 1, 2, 3, and 4. And basically all you have here is, we said, is you have the same thing. You have your impulse stages in the beginning. All right, transition's just going to be flipping it around. So that way it's just going to be transitioning it into a different type of turbine blade. All right, and that's the 4 reaction. All right, and that's your head turbine for your LP turbine. This is all used in a head steam. All right. Your stern steam is in this portion. Right here in the green. That's your stern steam. All right. Let me delete what's on here. Whoa. We should be going over. All right. So, like I said, your head rotation, your head steam goes through the ahead portion of it. It rotates in that direction. And of course, your stern steam is going to be rotating in the opposite direction. All right. So let's talk about nozzle control valves. Your nozzle control valves, as I talked about, is coming from your steam chest. That steam chest is going to be the portion where it's controlling all of the steam before it goes into your HP turbine. All right. So you have your C speed. That is used when you're out at sea, right? That is when you're basically at full speed. You are going from one port to another port. When you entering into a maneuvering phase, that is going to be when you enter into a port and you start to need to maneuver and change your speeds according to what's happening outside. All right. They're throttled at a fixed position. That position is usually wide open, but they can be throttled. Nozzle control valve opens a chamber to a set number of first stage nozzles. All right. And their numbers correspond to each one of these valves. So 9, 14, 12, and 4. Number of nozzles open corresponds to a particular engine RPM and hence C speed. All right. If you remember going back into last semester and how I was unable to answer questions onto what's the speed we're usually going in knots, and because engineers usually don't operate at knots. We operate at RPMs. We care about the RPMs of our engine because that's an actual physical thing that won't change. We can be going into crazy storms and we can be going into currents that are going against us, or we can be going with the current and everything else. But what really matters to us is something that will not change is our RPM. Sure, if we go with the current, our RPM might be going a little bit faster because it's not as much resistance. And same thing against it. But we'll know because of our RPM. All right. The knots of the ship that it's going is just can vary too much with too many conditions we don't know about. So we care about our RPMs. So, like I said, this is your sea chest, this whole area, the steam chest right here. Now, 9 correlates to 9 nozzles, just like how 12 will correlate to 12 nozzles. All right. If you want to go at different RPMs, you open up a different number of nozzles. All right. You can add them together. 9 and 4 is 13. Those are 2 nozzles will be open, nozzle 4 and nozzle 9. All right. If you want to go 14, you would open up the 14 nozzle. If you wanted to add 4 more to it and go 18, you would open up your nozzle label number 4, and those two together would be 18. All right. Any questions on that or what I've gone over so far? All right. Let me see what we have left in. All right, so let's go through the ahead and the stern. That way we finish up with our vapor side. And when we go into the liquid, before we go into that, we'll take a quick break. All right? So let's talk about your throttle box. All right, biggest thing, where it's located on the vessel. All right, you're coming in the main engine room level. There's your door. Right next to your door is your throttle box. All right, there's the 2 throttles. You would have the HP turbine right here. All right, and you have your LP turbine right next to it. All right, you have your both boilers sitting over here, and then your TGs over here. All right, but this is your throttle box. Now, right next to the throttle box is a valve that's hanging in the air, and you kind of have to look up at it. That's your stern guardian valve. All right, that's where that stern guardian valve is located, but your stern throttle and a head throttle are located in the throttle box that is quite literally right next to your door. All right. So what we have here is basically what's going to be controlling the amount of steam that goes into your HP and LP turbine. So your head throttle is going to be, in the name, it's going to throttle the steam They are not fully open and not fully closed. It's a throttle valve. All right. And it's going to match whatever RPM, a certain pressure entering into the steam chest will match a certain RPM at a given set of nozzles. Okay. But just know this throttle is like your gas pedal in your car. That's going to control your speed. So the more you open it, the more speed you have, the faster the steam goes through. Right? That's a big portion of it. The more you open it, the more steam is going to go through it, the faster it's going to go through. All right. Now, you close that all the way. Think about what's still happening. Your HP and LP turbines are still going to be spinning because of the momentum of the ship. These things are giant pieces of machinery. All right. They have a mass and they're going to stay in motion. All right. And that's the thing you have to think about when you're going to be slowing and trying to go into a reverse. And why this Astern Guardian valve exists. If you were to mistakenly open your stern throttle while your head throttle was going, you would have catastrophic problems in this LP turbine, and it would probably destroy a huge portion of the ship. All right. That's why this Astern Guardian valve exists. It's to protect just the general mistake. Right? It's to protect in case of leak by. All right. So if you were to open up that Astern throttle without opening up that Astern Guardian, we would have no steam flow. All right. The only time you would open this Astern Guardian is during maneuvering. That would be the only time that would be open while you were going to be operating your head and your stern at the same time. When you're maneuvering at sea, when you were going at sea speed and not maneuvering, that Astern Guardian valve is going to be completely closed. So that is basically the throttle valves in a nutshell as far as what you guys can see with it. All right. Any questions on that before we take a few minute break? All right. So let us take a 15-minute, 20-minute break about, let's start back up at 10:30. All right. And we'll go through the rest of these slides. All right. Everyone's back. Or everyone who has cameras is back. So let's talk about everything else in the steam water cycle. Let's talk about how we get from steam back to a liquid. All right. So remember, we're coming out of that LP turbine, and that LP turbine is going to handle both our head and our stern steam, not at the same time, but both are going to be going to that singular point. All right. From there, it's going to go into our shell and tube type heat exchanger. All right. We can use the salt water that our ship is flowing through to cool down any of the leftover steam and turn it back into a liquid. And we're doing this because a liquid is going to be a lot easier to handle. It's going to be a lot easier to manipulate, and to if we have to add any more liquid into it at a certain point, if we have to do any makeup feed into it, we lose any steam. All right, if we blow that steam whistle or anything like that, it's going to be easier to add any steam and add any liquid into a liquid already. All right, so we can utilize a saltwater pump, or we can utilize something called the scoop. All right, which is basically just it's a scoop underneath the ship. It's just a port that it just scoops up water, and it uses the ship's forward momentum to push water up through the condenser and out the other side. We don't need to use any mechanical pump at all. It's just a giant valve that opens up, and we just start taking in water. All right. So we have two things that can be pushing salt water through this main condenser: either the main saltwater pump that we have, or we can use a scoop. So as we talked about with, all heat exchangers in the world, it's all about what you're doing, your main idea of what you're trying to do in there, right? And we call this a condenser and not a heat exchanger, or we're not calling it our main heat exchanger. We're calling it our main condensers because we're talking about our fluid one is what we care about, our steam. All right. And that's what we're concentrating on. So that's what we're trying to do here. We're trying to condense that steam, so we call it a main condenser. All right. So fluid one is giving up its heat. Fluid two, which is our salt water, is absorbing the heat. It's taking in that heat from fluid one. All right. Our main purpose is not a fluid two. In this case, we only care about fluid one. We want that stuff to go from hot to warm, or from a gas to a liquid. All right. Now, with a shell and tube type heat exchanger, they do not make contact, just like other type of heat exchangers. They do not mix. They don't become a mixture. All right. They come in contact with each other by the outside of these tubes. They come in contact with each other just like if you had a radiator for your heating of your house. The steam inside that radiator is in contact with the air as much as the steam inside of fluid one is in contact with the salt water of fluid two. All right. There's a physical barrier in between, but they are doing heat exchanging. They do not mix. So the different types of heaters that we can have are heat exchangers. We have a heater, which is a primary fluid, does not change phase, but increases in temperature. All right. So it's like a fuel heater, lube oil heater, trying to heat the space of a room. Like we talked about a radiator. We have a cooler. Primary fluid does not change phase again, but decreases in temperature. So a lube oil cooler. What else can we have that we're trying to cool things? Your radiator of your car would be a cooler. All right. Your evaporators that we have. Primary fluid changes from a liquid to a vapor. All right. So the evaporator, that's what we call it, always an evaporator when we're talking about freshwater distilling. Now we're talking about a condenser, which the primary fluid changes from a vapor to a liquid. Remember, engineers like to label things of what it does. All right. If it's an evaporator, it's evaporating that main fluid. It's a condenser, you're trying to condense that fluid. If it's a heater, you're not trying to do any phase change. You're just trying to heat it up. All right. And the cooler, same thing. You're not trying to heat it up, but you're trying to just cool it down. All right. If you put an ice cube on your body, you're cooling yourself down. You're not changing the state of your body. All right. That would be a cooler. But if you look at the ice and become a primary, then you would be changing what it would be looking at. All right. It's all due to that primary fluid of what it is. So this is what our main condenser looks like. All right. Obviously, it's in 2D form. We have our main circulating pump that is pushing salt water through. Again, we could be utilizing a scoop. Salt water goes in, salt water goes out and goes overboard. We have no more use for it. It's done. All right. I'm sure if we wanted to do more efficiency, we can learn to do other things with it. But for this case, it goes overboard. It's done here. Then we have our main condensate pump. This is going to be sucking all the liquid, all of that fresh water that we just came from that boiler out to the rest of the steam water cycle as we've talked about. All right. The big thing here is when you guys go out on cruise, you will have to take a level of this. There will be a level bob. All right. This level in here is important for many reasons. One of which, and the most important is that you don't want this main condensate pump to draw air. It's not a positive displacement pump. Right? It won't be able to reprime itself. Right? So if you lose that, the rest of the steam water cycle goes out. All right. So this bob here is important to let you know of what speed you should be running these main condensate pumps. You don't want it to be filled up, so now you have a liquid level up here. You want down here to have a nice solid liquid level, so that way you don't break the seal. You don't let this pump become airbound. Now you can't. Oh, that was just an email. You don't want this main condensate pump to become airbound. Now you can't prime it again. You don't want to fill up this to the point where you lose heat exchanging. All right. And remember, the biggest thing here is that this is in a vacuum. If this becomes airbound, boom, all of a sudden you're adding a huge amount of air into the situation, and your air ejectors are not going to be sucking out anything. You're going to be losing vacuum. And now you're not creating more water. You're not creating more of a liquid. And now you're not condensing as easily, and you just lose your whole cycle. Not only do you lose your liquid end, but now you're going to start to lose what's going to be pulling all that steam into your condenser and through all of your HP turbines. All right. So, and then we have our air drag line. This is going to your air ejector. And the air ejector's main purpose is to pull out non-condensable gases. All right. Does that make sense as far as the main condenser? I know it's a lot to think about, but at the end of the day, it is turning a steam to a liquid. You remember nothing else but that today, it is a victory. All right. Steam to a liquid. All right. Air drag line. Air drag line goes to the air ejector, and that is going to be pulling out your non-condensable gases. Gases that cannot be condensed from steam to a liquid. All right. So let's talk about that main air ejector. So we have our condensate from our main condensate pump. Where is that located? That's located right here. Thanks for asking. So as we go through, we come from our main condensate pump. All right. We go through the main air ejector. Same thing, shell and tube type heat exchanger. But we are no longer the primary fluid. We are no longer that fluid one. So let's talk about that fluid one. This is what is physically happening inside. We are using auxiliary steam. And that auxiliary steam is going through a nozzle. And that nozzle has a Venturi effect. Remember, it's going to be sucking in and pulling whatever it's attached to. This is technically that low pressure over here. All right, here's your high pressure. And that low pressure is getting sucked in no matter what. Whatever is in that line, whatever is in that main condenser is going to be sucked in no matter what. And that's how you're going to get that low, low vacuum. All right. And it's mixing. Right here, it is mixing. You no longer have auxiliary steam and non-condensables. You have a mixture at this point forward. All right. And as it goes through, you're going to be gaining energy back. All right. Because now this auxiliary steam is crap. It's shit. You can't just throw it back into the, into the steam cycle. You can't just put it into the HP turbine and expect it to work. All right. So we want to grab some of that heat. And that heat is going to be returned back to your liquid, your main condensate. All right. So you're heating up that main condensate with that auxiliary steam, with the steam and the non-condensable gases that are being grabbed from your air ejector, from your main condenser. And this will return back to your main condenser as a loop seal. Because what you're going to try and do is you're going to try and just, one, get rid of that auxiliary steam and anything along the lines of just try and gain a little bit of that energy back. Same reason as why we're pushing your condensate through it, just to gain a little bit of that energy back. All right. Now we're going to talk about that second air ejector portion. It's a two-stage. All right. And what its job is to do is you're trying to pull out any of these non-condensable gases again. All right. And that whole effect is trying to just remove it. All right. And that's what this gooseneck is. All right. You put your hand up underneath it during cruise, I encourage you. It's not going to hurt. All right. It's not going to harm you in any way, but what you're going to be hit by is just little puffs. All right. It's just going to feel like, anybody ever see those air cannons you pull back? It's like those garbage can things. Kind of what it feels like, about that level of air pressure hitting your hand, maybe even a little lighter, depending. All right. It just full of non-condensable gases that are just puffing out of this thing. All right. So you have your inner condenser and you have your after condenser. All right. This is existing around 1 atmosphere. This is existing around 10 to 15 inches of mercury. So you're in vacuum. All right. This drains to your ADT, or your atmospheric drain tank. And then that condensate goes on its merry way. Just gets heated up a little bit more. All right. Do you guys understand the point of the main air ejector? This is trying to remove the non-condensable gases, trying to make that main condenser into a vacuum. All right. But what it's also trying to do is to give some of that energy back to your main feed water. All right. So it's doing double duty here. It's removing the non-condensable gases, but it's also trying to give a little bit of that energy back to the main condensate, back to your feed water. All right. That makes sense?
I do have a question about the auxiliary steam and non-condensable mix.
Okay.
So it goes through this. It comes out of the first stage, goes through. It returns to condenser via loop seal. Does the auxiliary steam go back into that condenser? Because the non-condensables would be taken out anyways if it did, right?
Yeah, so it's going to be, nothing's going to be perfect here. But like 99% of the non-condensable gases are going to be tried to be pulled out again. All right. But that auxiliary steam and maybe a little bit of that non-condensable gas, this is why you won't turn this system off. Oh, we have perfect vacuum. We can turn off the main air ejector. No, it's just going to be constantly running. So any of that steam or non-condensable gases that gets grabbed here, that auxiliary steam is going to return to the condenser, and it's going to be condensed and it's going to be turned into condensate and brought through. But if you think about it, you're not going to have, if we look at this, look how far it's going to be going down. It's not going to return, it's not going to enter in right here. all right, you're not going to be pulling in non-condensable gases because they're non-condensable, all right? So you don't have to worry about non-condensable gases going in here. The big worry is it affecting your vacuum, all right? So did that make sense? Did that help? Okay, good. All right. Again, guys, know this. Know where the liquid's coming in. Know where your main feed lines are coming in. All right. These should be drilled into your head. So when you go onto the ship and you look at a component, one, you should be able to understand the basics of what's happening in front of you. You should have this picture in your head when you look at that main air ejector. That way, these basics that are in your head can help you decipher what's in front of you. Because this is 2D, and when you get on the ship, it's 3D. You're walking around it. All right. So let's talk about the first stage heater. Even though we have it bypassed on the ship, from what I've been told, is that it just doesn't give that much efficiency. And for what it's worth, it's not really worth what we're doing. All right. But we should still learn about it anyway, because you may end up on a steamship. You still are getting your third steam's license. All right. You still can, end up in New York City running steam for Gen Ed, and basically these will still be used. All right. So it's 3 heat exchangers in 1 casing. All right. So your condensate is coming from your air ejector. So it's exiting that air ejector right here. And it pipes right into your first stage heater. All right. And again, it goes through these tubes and exits and goes to your DC heater. All right. That's the path it takes. So that LP turbine bleed comes off. It goes into the entire casing. All right. Your actual first stage heater. Bypass goes to your first stage drain cooler. All right. You have your gland exhaust condenser. Oh, I thought there was more. Never mind. And this is basically what you're doing. You're just trying to grab little pieces of heat from where you can in the system, and you're trying to stuff it into your condensate. All right. That's all you're trying to do here. Again, we just don't use it. There's really, what I've been told, there's no point to really use it. But the big thing to just remember about them is just they're basically 3 heat exchangers in 1 casing, and you're just trying to absorb heat from your components where you can get them. All right. So from that DC heater, from the first stage heater, we go to the DC heater. All right. So we're going way from the lowest part of the engine room all the way to the highest part of the engine room. This is a giant tank that looks like a big old soup can. All right. It is as high as possible as you can in the engine room. And we don't do this lightly. This thing is going to be full of liquid. All right. So liquid sloshing around at high points on a ship isn't good for stability if it wasn't for a damn good reason. All right. And that reason is because we're trying to use gravity to help us. We go to our feed pumps. We need those feed pumps, like we said, we need them to be above 600 PSI, the exit point, right? And anything we can do to help those feed pumps do that, we're going to do it, all right? And it's going to give all of that head pressure. All of this height is going to use gravity, the natural state of gravity, to give us head pressure. And all of that liquid that's in that DC heater is going to add to it. All right. So first stage heater condensate comes up, goes into the DC heater. It's basically the point of what we're doing here with the DC heater is we're spritzing it up. All right. It's like taking an aerosol can and just going into the air. All right. But instead of just letting it formulate and be into the air, we're going to hit it onto the side with auxiliary steam. All right. And what we're trying to do there, it's a scrubbing action. If you ever heard of like scrubbers and stuff like that, that's what we're doing here. We're scrubbing the steam to remove any of the dissolved O2 in the condensate. The DC heater is also known as the DFT, the de-aerating feed tank. All right. So we're like poofing it up into the air, and then we're hitting it onto the side. So that way we can remove any O2 from that condensate. All right. We want pure water, as pure as we can. All right. We don't want any variables going into our boiler. All right. Boilers and engineering doesn't like variables. We try to minimize as much as we can. All right. Feed water is approximately 15 psig. It's got 250 degrees Fahrenheit, and it acts as a surge tank as well. All right. It's a big tank of water. It's full of just in case. All right. If we needed a heck of a lot of steam at that moment, boom, we could add a huge amount of water into it, no problem. All right. It's all sitting at a nice high pressure. It's sitting at 250 degrees Fahrenheit. We don't have to heat it up because our distillate tanks are not going to be heated to 250 degrees Fahrenheit. All right. We could pull steam like that. The other aspect of it is that we can, if we don't need as much steam at that moment, well, we got room for all of that condensate that's coming out of the main condenser to be added somewhere. It's not like this is a direct pipe, like it's got to go somewhere. All right. This just gives us a nice little surge tank to move in any direction. All right. From there, it goes to the feed pump suction. Like I've said, give positive head to the feed pump. We want to give as much ability to these feed pumps to pack as much of a punch to get as much of that water into that boiler. All right. Any questions on DC heaters? All right. Am I going too fast, guys, or you guys all right? All right. So main feed pumps. Main feed pumps are not motor driven. All right. They're turbine driven. So they're going to be driven off of steam. All right. So we have our actual pump. So our DC heater has one feed, got a suction valve. Of course, we have to have a suction valve. We come out of the pump and we have two discharges. We have our main feed and our auxiliary feed discharge. They come out of the same pipe. They will be at the same pressure. All right. So we go from our DC heater. We open up our suction valve. We start up our pump. We can recirc to our DC heater down here. We have our steam supply. It's steam driven like I've talked about. All right. So both your main and your auxiliary will be able to go into your port and starboard boiler, just like I've talked about. Both will be operating at the same point, but both will have a main feed line and an auxiliary feed line. All right, let's talk about the port boiler. We're almost there. We're going to go into our economizer. These main feed and auxiliary feeds, all they do is the big difference is right there. We have our fresh water, our feed water regulating valve. All right. I'm not going to click it again and nothing's going to show up there. All right. That feed water regulating valve is not on the auxiliary feed. So that way you can physically control it. You know certain conditions are going to result in certain things that will happen inside the boiler, which you will learn about when you go out on cruise, because these conditions happen a lot. These auxiliary feeds will give you that control. all right? Because you can't battle out a regulating valve and win. If it's sensing something, oh, it's sensing something. It's on its way. Remember, it's only got that one input. All right. So you can actually control your boiler water level using your auxiliary feed. And it's coming from the same pressure, the same source. And that's why one goes to both boilers. All right. Go into our port boiler. We're going into our economizer. And from our economizer, we go to our steam drum. All right. Feed water is added to the steam drum, not to the water drum. So the economizer isn't really located there. It's more located inside of the boiler. Remember, it's where the stack is. All right. So basically, you're preheating your water before it actually enters the boiler. Even though it's inside of the boiler, it's before it enters your boiler. All right. So all of those gases, everything that you've used that goes through your generating tubes, through your superheater, back through your generating tubes, it has used a huge amount of energy and it barely can give any more. Well, we're going to give it through the economizer and we're going to try and take as much as we physically can out of it. All right. That's the whole point. That heat is still there for us to grab. All right. And if we look inside of that inside of that steam drum, which we just blew up right here, there's a whole mess of pipes. I want you to concentrate only on one of them. All right. That pipe right there that's coming out of the economizer. That is the water. That is your feed water that enters your boiler. All right. So that is the basic steam water cycle in a nutshell. We're going to talk about how that power goes from your turbines to your actual prop in a second. But does anybody have any questions before we move forward? All right. So let's talk about the turbine RPM does not equal our prop RPM. All right. It's much, much faster. All right. So we have our basically a double reduction gear setup. All right. So we say this is our HP turbine. All right. Come out of that HP turbine, we go into a pinion right here. This pinion is much smaller, and that pinion is going to attach and gear into a reduction gear. All right. The smaller pinion is going to spin at a faster speed, but have a lower torque. The reduction gear, the first reduction gear is going to spin at a slower speed, but what it's going to gain is torque. All right. And remember, speed is not what we're looking at in ships. Our main thing that we want is torque. The torque output of our propeller is where we get our forward momentum and our stern momentum. All right. And again, we're going to do the same thing. We go into another pinion and we go into a section reduction gear, which is called actually our bull gear. All right. And then from there, we go out and we go into direct shaft to the propeller. That is how our reduction gears are going to be working. And we're going to have another set for the LP turbine as well. Now, for anybody who's been down in the engine room, we have our thrust bearing. All right. This thrust bearing is massive. The nuts on it are like this big. All right. The bolts are massive as well. And that is our physical location. The thrust that is produced from that propeller goes into that thrust bearing, into those bolts. And that is the point where the ship is being pushed through the water. All right. That is the singular point on the ship, which takes all the thrust and moves that vessel. All right. The next thing we have are line shaft bearings. The job of the line shaft bearings is just to keep the line shaft in orientation. All right. Obviously, with metal to metal contact, we need to keep them lubricated, so it's a bearing. But it's basically just keeping the line shaft up, all right? And then we have the stern tube bearing. All that's doing, keeping that salt water out and keeping the atmosphere in, all right? That's all the line shaft, the stern tube bearing is for. Now, a propeller, obviously, ahead, we're going ahead, and a stern, we go astern. So what about those LP turbines, I hear you ask? Well, let's talk about it. So we have our HP and our LP turbine, all right? Both will go through double reduction, and both will meet up to this bowl gear right here, this large reduction gear, all right? Now, they will have to spin. When they get to this position, that reduction gear has to spin at the same speed. It's geared into two different pieces of machinery. All right. We'll talk about how that's happening in a second. But if we look at it, we have our high pressure, high speed pinion. We go to our high pressure first reduction gear, which leads us to a high pressure, low speed pinion. And then we go to our common bolt gear. Same thing over here. We have our low pressure, high speed pinion, goes to our first reduction gear. Then we have our low pressure, low speed pinion, goes to our bolt gear. All right. So our head steam will go through our HP turbine and our LP turbine, and energy will go through and go to our bolt gear. But with the astern, the HP turbine is basically going to go for a ride. All right. There is no decoupling. It's not like that's going to be geared off. The HP turbine is just going to spin reverse with nothing kind of going on. And that's about it. All right. So basically, you can use reduction gears in many different applications. Usually it's used in a direct, it can be used in direct shaft. It could be used in generation of electrical power. You can use them anywhere. All right. Just don't use them on mousetrap cars. It doesn't work. I've tried. So you can use them in jet turbines. You can use them in medium speed diesels where you want to put some torque out so you can create your generators. All right. You can use them for steam systems that we've been doing to create an electric drive, but you're using steam to create the power instead of like a diesel engine. All right. So basically that's it for the bowl gears and everything. We'll learn more when we go on cruise. I'm sure when you guys will see everything moving, a lot of things will just kind of make sense. I know the feeling of just trying to picture something that massive, that's that quiet right now, will be moving. All right. Last but not least, before we end the day, let's talk about the EOT, the engine order telegraph. Big thing here. Biggest thing to get into your guys' head with your EOT and control of the engine room. The bridge has their EOT. All right. Their engine room telegraph. It does not control the speed of the engines. All right. It does not control the speed of the engines. What it does is it sends a request to the engineers to change the speed of the engines. All right. That is the biggest thing here. Diesel ships, yeah, give them control. Let them go to town. They're not going to break anything. Steamships, we need to have control over it because there's so much going on. There's so many moving parts. And I don't mean it like in the literal sense of turbines spinning and water moving around and all this kind of other stuff. There's physical human elements that have to be added and knowledge that has to go into it in order to change speed. All right. So you have your engine order telegraphs. So they're a request. All right. We have one that looks like, basically looks like a small clock. It's located next to the, how's it located? It's right attached to the throttle box as soon as you walk into the engine room. All right. The bridge has two of them, I believe. They're up on the bridge. somewhere. And basically what they do is they will ring a request, all right? Whether it be a stern or a head, they have their speeds that they're asking. We have a certain RPM that's attached to that speed name, all right? And basically it's a little bell that will ring continuously, and you go until you go, hey, we have matched the speed, or, you know, we acknowledge that this is what you want, all right? So they'll move it around and we'll match it. So they have theirs. Theirs is their input, is this the big piece they can actually input into it. Where we're at is the blue arrow, all right, and vice versa in the engine room, all right? So that's what we're going to be having. The input is always where you're at, and then whatever the smaller arrow is, or whatever you can't control in that spot is what's coming from the other location, all right? So biggest thing with what we have is when you operate the messenger point on this, you will get an order that says go full ahead, all right, from half ahead. Biggest thing of what you got to do is you got to shout to not only the people that are operating the throttle box, but you got to shout all the way across the turbines to the men operating and the women operating boilers. All right. So they can predict what's going to happen inside of those boilers due to experience and knowledge. They will know if we're going from slow ahead to full ahead with no clicking in between, they're going to need a lot more steam because you're going to be opening those throttles a lot more than you would if you were to have a slow ahead. So we're going to run out of steam if we're not careful. So they have to produce more steam. All right, and that's the reason you have to yell to the men or the women operating the boilers, not only to the people working the throttle box. All right. And as we talked about, you know, in the past, people who were not officers in the Merchant Marine tended to be, you know, non-educated, things like that. Even when you went into the Navy, when they were steamships. So they had to not rely on people who could read and write, but they can operate on symbols. All right, and that's where these symbols come from. All right. So we have a head, and our head looks like this arrow here. All right. So we have our emergency full, which is the full symbol with an E next to it. We have our full, we have half, and we have slow. And then we have dead slow. All right. This line right here is going to be representing which way we want to be going. All right. That's why we always would have one. All right. So slow is always going to have one line and then just build up from there. It's a good way to remember. And then basically same thing, but a stern, just the opposite direction. You don't have to do two different colors. No one's going to ask you to. All right. Then you have standby, which is a triangle or just standby. And then you have stop, which is an O or an X. And then you have your last symbol that's not talked about here, which is finish with engine or FWE. All right. That just means we're tied up along the dock and you guys can shut down, or, you know, we're done maneuvering. You guys can go at full sea speed. That's what that means. All right. Bell book. Here's an example of the bell book. All right. A lot of the stuff is just going to be told to you to write down, such as where your arrival is, the, you know, date, write the date, the arrival time of what time you arrive, coordinates. And this is basically going to be what the maneuvering looks like. All right. So it's going to be like, we're going to go slow ahead at 0730. We're going to stop at 0636. Then we're going to go full ahead at 0741. All right. And this is basically what's happening. You can ring these things up pretty quick. I mean, look, we're going from full ahead to slow ahead to half ahead to stop to half astern to full astern to stop to slow astern to stop to dead slow ahead. Like, they want us to change a lot. And this is why it's so important to, you know, that we control those engine speeds. All right. And then again, as I talked about, FWE, finish with engines, we have arrived. All right. that is it. That is the steam water cycle there, and everything in between. All right, you guys are masters of steam now. So, any questions?
What's the difference between emergency full and just full?
It could be the speed. Basically, your emergency full could be like it could be coming out of a stern. So you wouldn't be going from, it's all condition based. All right. So if say you're at slow ahead, all right, and you're maneuvering, and all of a sudden they're like, oh man, we're coming in a little too fast. So we'll go stop and then we'll click over to slow ahead and try and slow ourselves down. And then all of a sudden it's like that happened pretty quick. So now it's going to go to half ahead and full ahead. Like it's not quick enough. And all of a sudden they realize they might hit something. You're basically, what it represents is they're going to go all the way to full astern and then all the way, and they're going to skip everything in between. They're going to go and click full astern and they're going to click to full ahead. And that basically means get us full ahead as quick as you can. All right. That means that we are going to be not treating the engines nice. All right. Again, it's used in emergencies. So you're going to basically just be, the way you normally slow down a turbine is going to be slowly blasting it with whatever steam is going in the opposite direction of what it's going in at that moment. All right, just a little quick blast. And it's the same idea of like slowing down your bicycle. All right, you kind of click that brake a little bit. You don't just clench on it. Well, if you're about to hit into a car, you're going to clench on it no matter what. All right, and that's the same idea of what we would be doing with emergency full ahead and vice versa with emergency full astern. All right. It's going to be just hit that turbine with steam. As soon as it stops, just blast it with steam and trying to basically get whatever motion via either emergency ahead or emergency astern going as quick as possible, and try and stop the ship from doing whatever you don't want it to do, which is probably going to hit something. All right. That's what those are going to be used for. It's not like they have a different speed. It's just the quickness of it. All right. Any other questions? All right. So again, guys,